Hello guys, my name is Arun and welcome to my channel. This series is a series of tutorials on OpenMP implementation in Fortran. Now, in the last tutorial, we saw an example of how to do um, OpenMP parallel do loop. Today, I thought of explaining you guys about two concepts, namely parallel and private and shared classes available in parallel do loop, and I also thought of explaining you guys a concept called as coarse grain parallelism that can be done in OpenMP. I mean it's not an OpenMP procedure, let's say, but it's a kind of a principle wherein you used to do a job, used to do a certain job or a problem. Okay, now coarse grain parallelism is as follows. Now what it does is that let's say you just take a big chunk of a problem or a big job and a big problem, and then divide it into big pieces or divide it into big chunks, okay, and make each core or thread work on a particular piece, and that is called as coarse grain parallelism, wherein you manually specify which parts to be done by which code and which can be done by which code. Now one example of coarse grain parallelism is during loops. Now what I'm saying is, let's say you have a loop, say I equals 1 to 100, 1 to 100, and you have like n threads. Now what coarse grain parallelism says is that you just write a single piece of code. Okay, yeah, it's like a do loops, like something like do I equals I start to I end, okay, and do, and you do some you do some operations over here, but just this one single set of instruction. But when you do this, okay, each thread each thread does the same instruction, but when doing the same instruction they'll be working on a similar one chunk of a problem, meaning for instance, uh, uh, thread number 1, n equals 0, might work for I equals 1 to 25, n equals 1 might work on I equals 26 to 50, n equals 2 might work for I equals 51 to 75, this is a 2, okay, and then n equals 3 might work on I equals 76 to 100. Okay, but you don't write separate loops for them, you just write the same instruction. The only thing you'll do is that you'll just change the value of I start and I end for each of these loops, each of these variables, and this is an example of coarse grain parallelism, and that's what we're going to do over here. So what we're going to do in this example is that I'm going to calculate do the trigonometric identity, sine square theta by cos square theta, sine square theta by cos square theta. Okay, now what I have here is that I just have, now let me scroll this a bit. What I have here is I just have a length L, okay, length L, and I'm trying to fit a sine wave within the length L. Okay, sine wave and a cos wave together within the length L. So what I do is that I'll just divide this length into discrete number of points, and let the number of points be m. So for instance, let me keep m equals 4. So that being the case, if m equals 4, the distance between these points is actually L divided by m minus 1. Okay, so if this is L, this will be L by 3, and this is again L by 3. These will be L by 3, and that's it, and there you go. These are distances. Now what I'm going to do is that I'm going to measure the distance from this end till this end for each point. I'm going to measure the distance from the one end to the other end. Okay, one end to other end, and then I'm going to calculate the value for a. For every value of a, okay, I'm going to calculate the value of xi, and then I'm going to plug in sine square 2 pi xi divided by L plus, I'm going to do this one, plus cos square of 2 pi xi divided by L. I'm going to do this and store it in each value. This is what I'm going to do. Okay, fair enough. Okay, now let's see how this program works. Okay, now I have num threads to be 4, setting m to be 4, and I have m values between n values. I can change the value of m anytime I want. So I use the value of m to set the value of the matrix A, means size of matrix A, and then this is the pi, and these are the do loop iterators I'm going to use, which I talked about before. Okay, so I start an in, and thread num is actually for storing threads and getting the value of the thread ID. Okay, and t1, t2 and ep are the timing variables we saw in the previous tutorial. I is the iterating variable, and dx, l and x are length parameters, and ppt is the points per thread. Here for this loop I from 1 to 100, and for 4 threads, each thread takes like 25 points and work on it or 25 iterations of the total 100 iterations. So this value ppt is going to give me the value of the total points per thread. Okay, and I'm setting the value of a to 0 to start with, and then I set the value of dx. Okay, and dx I set the values over here. This is L by 3, that's it. And let's calculate ppt. Now ppt is actually m plus a number of threads minus 1 divided by number of threads. So what it says is that let's take a simple value, m equals 16, let's say, and n equals 4. Now ppt will be equal to m plus n minus 1 divided by n. So this will be 20 plus 4 minus 1, so 19 by 4. So this will be 4.75. This will be 4.75. Okay, but since ppt is defined to be an integer on the top, the decimal part of it will be truncated. So this will be just 4. ppt will be 4. Now if I were to use 4 threads, the thread numbers are 0, 1, 2, 3, and we have I start, I end. Okay, now I start is given by thread num times ppt plus 1. So thread number is 0. For this one, thread number is 0. So thread num times ppt is 0. That plus 1 is 1. Okay, I end is minimum of m, and thread num times ppt plus ppt. So thread num is 0. 0 times ppt is 0 plus ppt is 4. So I end is 4. For thread number 1, this expression will be 1 times 4 plus 1, so it's 5, and this will be 1 times 4 plus 4, this is 8, and for this will be 2 times 4, 8 plus 1, 9, and this is 2 times 4 plus 4, so which is 12, and this will be 3 times 4, 12 plus 4, 12 plus 1, 13, 13, and this will be let's say 3 times 4, 12, 12 plus 4, 12 plus 4, 16, minimum of 16 comma 16, so it's 16 again, so this will be 16. So if you look at it, this loop gets nicely divided between 4 threads. Similarly, if we approach this approximation, even if you have multiple threads, they will just split the loop accordingly between our multiple threads. Now the problem here is that I get the value of x, no problem. I can get the value of I, no problem. So if I were to run this serially, if I said I start equals 1 and I end equals m, and if I do this loop serially, it's not going to be a problem because it's serial dependence, so it's not a problem. At least so at least the serial code will work fine. But the problem is when I run this parallelly, I have this big trouble of race condition. Meaning, let's say the thread 0 is active and it executes thread num, and thread num value sets up a particular gets a particular value. Now let's say it's thread 0, it becomes 0. Now even before the thread 0 can start this line, start working on this line, this thread num could have been modified, by some other processor, isn't it? Now the problem here is, instead of doing that, okay, the problem here is that this thread num is is in a part of RAM, is in the part of a memory which is accessible by all the 4 threads. They all can go and fight it, and they all can go and manipulate it and manage it, and that's why you get the race condition issue over here. They can manage. On the other hand, what if let's talk about this idea. I have my thread num over here, which is the original one, and then what I do is that let me allocate 4 more slots, and these are thread num 1, thread num 2, thn 3, and thn 0 for 0, 1, 2, 3. And what I do is that initially I just copy the value to here. First time I just copy the values to here, and then I have my processors, okay, and each processor just manipulates with just one of them. What I do is that I just what I'm simply saying is that let me create 4 more empty memory slots, allocate 4 more memory slots, and copy the value of this original thread num to each of these memory slots, and then use these and let the processors use these values, okay, and use one value alone, like one of this memory processor, one of this memory location is allocated for one processor, one for one processor, like that, one for each processor, and none of the other processors can go and manipulate it. Only the particular processor can go and manipulate it. Now if you do that, if we go by that condition, even if the threads start fighting with each other, okay, the thread values start getting modified and everything, the thread values, instead of going over here for each processor, the thread values will go sit over here, and here, and when they want to access thread num for calculating I start, instead of they referring to over here and modifying the memory over here, they just go and refer the values over here. Thereby they will not be modifying the memory content over here, okay. And to make sure that I start and does not disturb, does not go with the same way, I have to allocate a separate private memory allocation for I end and I start as well. And here, since x is depending on I, okay, I need a separate memory location for x, okay, and I is also varying for different loops and different threads, so I need a different separate memory location, private copy of I. So that's what private does. This private class, what it does is that it just creates private copies for each and every thread that is under each and every thread. Like if I put I start, I end, thread num, I and x, then what it do is that for each and every thread that is active, a private copy of these 5 variables will be made for each one of the thread, and the initial value of all of this will be taken from the already existing value that's been provided before. If those values are not existing, then those values are copied, and if those values are not existing, then the allocation is just made so that the threads can go and modify them if they want. Modify them when they want. And because of this, you're avoiding the race condition, because you're just when one of the threads wanted to occupy the variable, you're putting a condition stating that, hey, you already have this variable with you, right? So go on, access that variable instead of this variable, so that part is done. So that part is taken care of. Okay. Now because of this, if you look at it, since your I start and I end have separate copies for each and every thread, though the instruction is the same, they'll be operating on different portions of the loop. different portions of the problem. You're just operating on, they have the same single instruction, but you're operating on different chunks of the same problem, and that's why you call it coarse grain parallelism. You divide the problem into you divide a big problem into smaller chunks, and each chunk has been acted upon by your thread or your processor. Okay, that's why this is called as coarse grain parallelism. Okay, and here's the thing. That's why private class is useful for, like, if you put any variable in private, each thread will have its own copy, so it will not try to access some other copy of some other thread and cause any race condition issues. So that's taken care of. What shared does is the exact opposite. It keeps it keeps the values common for all the threads to access and modify. So L, dx, A and PP, especially L, dx and PPT, they're not going to be modified by any of the threads during this parallel operation, so it can be shared, no problem. Whereas A, it is being accessed and modified by all the threads, so one might need to think of keeping A to be private, but the fact is, because since I start, I end are made private, they're not going to access all they're not going to have any race condition on, they're not going to, the race condition will not affect on any part of A, so A can be shared, no problem. And then there is this class called as default class. What it does is that in generally when you run a parallel block, you might not know which variable to privatize, which variable to keep it private, which variable to share and all. So what default class is that, it just gives you an idea like what to do in case of a trouble. Like if you just put default none, then what will happen is that the parallel code will not assume any private or shared strategy for all the variables within the thread. Then if you put, then you have to explicitly specify all the variables that you put between the threads, put it between the parallel block. Okay. On the other hand, if I put parallel over here, not parallel, if I put private over here, then what will happen is that all the variables between this parallel block will be default, will have a separate copy for each thread, so they will be working on that part alone, so all the variables will be private for each thread, and that's it. And you also have this option shared. When you do shared, all the variables will not the variables will be just there in the memory, and each thread will not have its own private copy, so the values are prone to race condition unless otherwise you program them in such a manner that you avoid it. So that's the thing. So that's what I'm doing over here, and I calculate the sine square theta and cos square theta, and then just to give you guys an idea like how to get this value printed. To get this value printed, I'm using this OMP critical block, so that I'm just printing the thread number, which iteration it starts, which iteration it ends. We're using this OMP critical block, and then I close the parallel block, and I just use the timing routines which we discussed last time to calculate the time taken. And then for short values of arrays, I can just print the value of A. Since A just M is 16, it's okay, we can print it. It won't be that difficult. But if you're using a large number of arrays, then our output screen will be flooded with information, so I don't want that. So okay, that's it. And similarly, just like the shell script I wrote last time for running the code in serial as well as parallelly, I made a code here. So let's run this code and see what's happening. If I run bash code, if you look at all the values, all of them are 1 or close to 1. This remaining part is because of numerical precision, so don't worry about the 1. But the time taken is actually 0 seconds. Since this is OMP critical and this print block is defined under a compiler directive thing, so this will not come under parallel execution, so don't worry about it. On the other hand, now let's run this in parallel. Now when you run this in parallel, you get this value. Thread num for the thread number 1, the iteration starts with 5 and ends with 8. and for thread number 3 the iteration starts with 13 and ends with 16. You can cross verify it. For 2 it starts at 9 and ends at 12, and for 0 it starts at 1 and ends at 4, just like what we calculated over here. So this shows clearly that our calculations are working fine and everything. Now what we can do is that we can just comment this line out, because because it's working fine, so we don't have to worry about it. And let's increase the value of m. Instead of 16, which is like quite small, let's amp this up with a very large value, so that we notice some changes. Okay, we don't notice much, we just note some changes in milliseconds. Okay, hopefully this should cause some change. Okay, this took about 2.114 seconds during parallel execution. During a parallel execution, so if I were to do this in serially, ideally this should be done within 10 seconds or something. We should get a, let's see how much time it takes. It took about 7.55 seconds. So if I take a calculator and calculate this, 7.552 divided by 2.114, I get a speed up of 3.75. Like it's not completely 4. Okay, it's not perfectly 4 because of the time taken for the forking and joining operations. And by the way, if you guys watching this video without looking at my the 0th video, which is computer terminologies for high performance computing S1, the basic idea behind OpenMP, Amdahl's law, and speed up. If you haven't looked at this and you're watching this series, you might not understand what forking and joining is. If you want to know, just go and have a look at that video. Okay, have a look at that video. On the other hand, if you guys looked at it, just ignore this and carry on. Like what I mean is, like you noticed the speed up is not perfectly 4, it is close to 4. It is around 3.5. The reason this is because there is it takes a little bit of time. There is a little bit of time that gets involved for dividing the job and joining the job. It takes a little bit of time for forking and joining to happen, and that's why it takes a little bit of time. Okay, and that time when it is appreciable when compared to the computation time, then you notice the speed up not being perfect. On the other hand, if the computation time is much larger, then you will not. Then this forking time will be smaller. For instance, let's put up in this way. Let's say your computation time in serially is like 120 seconds. Let's say, and you're using 4 threads. Suppose so the maximum time it could have happened if this is in serially. Okay, let's say this entire section. Let's say if you were to do this parallelly, the minimum time t parallel minimum will be 30 seconds. Okay, if you do this perfectly properly. But on the other hand, when you do a parallel threading, what will happen is that this 120 seconds will be divided by 4, plus you have n1 times time for forking, plus n1 times time for joining, where tf is the time for forking, time for a single forking, and tj is the time for joining. Okay, so if I look at that, so this will be 30 plus, let's say for convenience I'll say for this program we're just having only one fork and one join, so we have like so n1 is 1, so 1 times the time taken for forking, let's keep it as 3 seconds, let's say. So 1 times 3 plus 1 times, let's say time taken for joining is 3 seconds as well. So this will take another 3 seconds. So what we have is that we will have like 36 seconds here. So your speed up will be 120 divided by 36. So let me take my calculator again. 120 divided by 36. So I'm getting a speed up of 3.33. Why? It's because it took some time for the forking and joining to take place. So that's why you're getting a slight push in speed up. Other than this, the other possible thing is that another possible reason for your speed up not achieving perfectly is because of your your threads being doing multiple jobs at a time. So if you look at it, whenever you run a job, it's not like one single thread will concentrate the job. There are like several hundreds of processes that will be running in your system. This is an example of what's happening in my laptop right now. There are like several background processes running, and a single thread will not work on a single process for a long time. It will work on a process for some time and then shift the job to some other thread. So there are some time it takes for shifting the job between one thread and another. So they might contribute some delays, and if one process is busy, the job might be on hold for quite some time, and those kind of stuff. Because of this reason, and because of threading and joining, you might not get a perfect speed up with that is corresponding to your processor, but it's always worth to try. And you might approach that when your computation time is greater and several times greater than your forking and joining time. For instance, this is for 120 seconds. Imagine your computation time is t. Let me zoom this up. Imagine for your serial time is 1200 seconds, and you're using 4 threads. Now TP minimum is actually 300 seconds, but your TP, what you'll get, your minimum TP that you can achieve is 300 seconds. Okay, what your TP minimum is 1200 divided by 4, plus, looking at the same example, you took one fork and one joining, and time taken for forking and time taken for joining. Let's keep it as 3 seconds as it is. So this is 1 times 3 plus 1 times 3. So this is 306 seconds. So here the speed up will be 1200 divided by 306. So if I were to calculate this up, 1200 divided by 306, this is 3.96. What I'm saying is this is approaching 4. All I can say is this is approaching a theoretical speed up, but your actual practical speed up might be a little more smaller, because there might be some delays with the threading and forking and joining, and process shifting the job from one process to another, something like that, and some process issues like this and stuff. Okay, that's all I have for you guys in this tutorial. Thank you guys for watching, and in the next tutorial I'll come up with another interesting topic to look at. Till then, take care and see you guys later.